So let's get started. Our last speaker is Joseph Renes from ETH Zurich. He will talk about Holevo's conjecture. Joe, please.
Yeah, thanks a lot, Hao-Chung, for this introduction. So yeah, I'm going to talk about, error exponents of channel coding. Actually, it's going to be related, based on some uncertainty relations. And this is a merge submission, actually. So it's not joint work. It was independent work. So between myself and also Ke Li and Dong Yang, as you see here. So in the meantime, both our papers are published, actually. Anyway, so of the 3 talks in this session, this is the one where we did not consult with Omar. And I think probably we would have gotten this faster if we had. But anyway, so we didn't do that. Anyway, so here's a little picture of, this is actually from Gallagher's book on when he's describing the error exponent. But let me tell you what that is. And yeah, okay. So the talk is kind of for all backgrounds, so just to make sure we're on the same page, actually in comparison to the first talk, right? We're going to consider channel coding over many copies of the channel, just one round of encoding and decoding. And when you do this, as the number of channel uses increases, you expect that the success probability increases with that n. And in fact, the error probability is decreasing, and in fact, it's decaying exponentially. And the rate of the decay is actually the error exponent. Okay, so there it is, EW of R. So it depends on the channel, W, and also the rate that you want to communicate, okay? Obviously, it's not going to work if you're trying to communicate above the capacity. Okay, so that doesn't work. Okay, so what's known about this in the simplest cases? So this talk is considering the simplest coding problems. So for classical channels, W, we have the achievability. This bound actually is usually called the achievability result from Fano and Gallagher and so on. And so here's the expression for it. And we're not going to go into the details of this expression, but I just wanted to show you that it depends on this. In fact, it's a Renes entropy. If you're not sure is this a bar or tilde? I can't remember. And some arrows. There's a lot of decoration here. Let's not worry about that. That's another like half-hour or 2-hour talk or something. But anyway, it's the input-output statistics of the channel, basically, is what's being measured. And that's what appears in this term here. And then on the other side, Shannon, Gallagher, and Berlekamp showed this sphere packing bound, I believe. And so you see in the classical case, it's actually almost the same expression, right? So you see it's just the range of the optimization that's different. And if you're above a certain critical rate, that was mentioned actually, then the 2 bounds will match. Okay, that's the generic case, sort of. That there's a sort of critical rate, and above it the bounds match, and below it they're different. Actually, when you go very below it, the critical rate, you're starting to go into the direction of 0 error, and so things are getting wild. Okay. Now, so we're just going to do the next most difficult case. Okay, classical quantum channel. What do we have here? So actually, I think this is from 2016 or something like that, Marco Delay showed the sort of quantum sphere packing bound. Exact same expression. So it's now just that the channel output is quantum. So this B system, instead of, I don't know, Y or something, it's now some quantum system B. So, but otherwise it's the same expression as the sphere packing bound. And already in the late 90s, so around the turn of the century, I guess, Renes and Holevo had showed that you could achieve this error exponent for pure state channels. Okay, so when the output of the classical quantum channel is just a pure state, or I mean, for every input you get a pure state. And Holevo conjectured that this should be true for all CQ channels. And then that's where it stayed for a while. I mean, people have worked on it, but we haven't come to any conclusion on this. until now. So now I tell you that, in fact, this expression works for all CQ channels. And that's the result of these papers. Okay, so here I just kludged together the archive numbers of our two papers. I don't know if it was that funny, but okay. They happen to have an 8 in common in the back there. Anyway, okay, so now what's the strategy for showing this? Well, in the classical case, you kind of carefully analyze the performance of the optimal decoder. We would think like, okay, or maybe some suitable decoder, something that's close enough to the optimal case. And that is, whoops, wrong button. That is not what we're going to do at all here. So we're going to make a statement about the optimal decoder, but we're not going to touch it at all, okay? So that seems strange. The way we're going to argue instead is via reduction, okay? So we're going to go from channel coding, the channel coding problem that we're interested in, to privacy amplification. And that's this gray arrow here, is this sort of reduction. And this is going to involve some uncertainty relations, or certainty relations, depending on how you want to call it. And then we're going to apply a bound on error exponent for privacy amplification that Hayashi has already, I think in 2015 perhaps, derived. And then, actually those first two steps will work for a subclass of channels. So the first two parts, you're almost there, but then you need to do some work to get to arbitrary channels, just the last little bit. But the heavy lifting is really these two parts. Okay, good. So for the rest of the talk, this is just the basic plan. And let me tell you first about the entropic uncertainty relations, and then how to do the reduction, and then we'll look at some ideas of the proof, or the details of the proof. Okay. So many of you will be familiar with entropic uncertainty relations. So the setting is that you have some tripartite state, psi ABC. So there's this box that's preparing the state, I guess, and it's outputting these three different systems. And on system A, which is kind of singled out here because it points down, points down, you can make one of two measurements. You can measure in the z basis, that's this little blue arrow, or you can measure in the x basis, let's say. And just imagine it's a qubit, and so it's really the z and x basis. We want it to be completely complementary or conjugate for this talk. So you have two bases, and if they don't, uncertainty relations like, well, you made some non-commuting measurements, surely you can't know both measurement results, right? So the entropic ones are saying, yes, indeed, the sum of the entropies of these measurement results is lower bounded by something. Okay. In this case, it happens to be log d. And actually, there's many extensions of this. So it's not just about the entropy of the measurement results, but also even the conditional entropy. So if you wanted to try and so this entropy here of the z random variable, the measurement result, conditioned on access to system B. So you could make some measurement on system B to try and reduce your entropy, but anyway, it's captured by this conditional entropy. But the sum of these entropies will still be bounded. And also, the guessing probability of how well you can guess this value, this measurement result, by making a measurement on system B, will be related to how decoupled the other system is, C, from the other measurement result. So here's the fidelity of that marginal state to the state where it's a product state and the X is actually maximally mixed. So that's what pi means. Pi is not a permutation here. There's no permutations. This is just the maximally mixed state. So this is saying if this side looks completely decoupled and this is random here, then this side you can perfectly guess on this side. And there's Renes entropy versions and on and on. Okay, so there's a lot of entropic uncertainty relations. Here I just put a little. So there's a notion of a dual entropy. So I just put that with this little perpendicular thing. Okay. Now, what we're going to use here is actually kind of, I don't know what you want to call it, maybe entropic certainty relation or entropic uncertainty equality or something, where all those inequalities we had before are actually equalities. Okay, so for certain states, this can happen. All right, we'll come back to this in a bit. But what we had before, let me just go back to that. No. Okay, here. This is good for crypto, basically, because you can prove that, like, you can, this bound here is not good for coding, right? Because what we want in coding is to lower bound the guessing probability, right? But it's good for crypto because you can lower bound this, you can make sure this fidelity is very high so that the state is very decoupled, okay? So that's good for crypto, but if we have these kind of equality or some inequality, the reverse inequality, then it will be good for coding. And so in fact, in the case we're considering, this CQ channel coding, we will have these equalities here. And so we will be able to actually go from this side, we can make a statement about this side and then infer something useful about the guessing probability. So that's the basic idea of the way to use the uncertainty relation. Okay, so now let's talk about the reduction, a little bit of the details of the reduction. So here we consider, again, the n uses of the channel. So here I just rolled them up into one box. And we're going to actually imagine that we just put in a uniform random variable to the channel, but also keep a copy at the input. So we have this blue box, which just generates random variable, copies it, outputs one to the left, one to the right. So one of them goes into the channel, and altogether we now have a CQ state, right? The thing going out to the left is classical. The stuff coming out to the right is quantum. Okay, so on this CQ state, we can, okay, I should actually tell you in advance, the reduction is in 2 steps. First, we go from coding to this task of information reconciliation, and then we go from information reconciliation to privacy amplification. So here's the first step. We started with the kind of coding situation where we've got the channel, and we converted, we made up a CQ state. Now we're going to consider information reconciliation. So the question would be like, okay, if I've got this output and you've got that one, how much information do you have to send to me so that I will be able to reconstruct the value you have? Okay, and the way you can do that is you take the output that you have and you hash it. You just run it through a hash function. And then the output, send the output to me, and I will try to decode. Okay, and here I've drawn this where it's a kind of reversible hash function. So these 2 outputs, the going up and the one going to the left, together they completely determine what this value is. I mean, for any hash function, you can make that up, right? You can just, I mean, you could just append the input here to there, but we can do it in a little more economical way. We'll see that in a minute. Okay, and then if you want to do, like, now we come to like this reduction of channel coding to information reconciliation. So the statement is really like, if you can do information reconciliation, you can do this channel coding. And the way you do that is you just run this hash function in reverse now. And since it specifies the input, like if you had this output and that one, then you're kind of back into this situation. But now in order to do the coding scenario, you actually break this link and just fix one of the inputs. Because what's happening in the information reconciliation statement is you want the decoder output to be equal to this one on average. And the average is going to be over these values. One of those values is good. I mean, it has an error probability at least as low as the average. And so you just pick that value. So here I just called it 0. And so now you have a coding scheme, because this is just the encoder and this is the decoder. Okay, so if you can construct this information reconciliation protocol, you can construct the coding protocol. All right, now we need to reduce to privacy amplification. And we need to speed up. So let's just look at this CQ state again. And now we'll use the uncertainty relation. So we'll think of the CQ state as actually coming from, we'll just purify it. And so the extra system, the arrows to the left and the right, they're the same down here, but now there's an extra E system. Okay, so now what we can do is, again, consider a hash function and maybe reversible hash function. And it splits this A system, so there's n systems here. Remember, we have our n-fold channel. So there's actually n copies of what I'll now call the system A. And this reversible hash function is going to split it into two parts, A hat and A check. And now what we want is, if we can construct this hash function such that this A hat is, if you measure it in one basis, in the x basis, it's decoupled. Now we can use this certainty relation. So this is the privacy amplification statement. So if you can show that that's close to 1, then by the certainty relation, so to speak, then you know that the guessing probability of all the rest of the stuff, the other outputs here, for the other observable will be, it's equal to that. So in fact, it turns out to be that you can just measure in the z basis. You can measure both of them, in fact. The fact that this one you can just convert to the z measurement, that's a technical thing. We'll not worry about that here. But anyway, now we have our statement that we want on, if we can construct this, we can get something for coding. All right? Good. So that's the information reconciliation part. Then we go backwards from that to coding, and then we're done. Okay? So the question is just how to get to this, right? This statement. Okay. Right. So that would construct the decoder for us, and so on. That's what I just said. Okay, so now in the few minutes that's left, let me give you a little bit more of the details. All right. Okay. So here's, it was 2015. Yes. So here's the statement that we're going to start from, so that this, if you use universal hashing, you can achieve not the fidelity, but this is the relative entropy, a relative entropy statement instead of fidelity. But you can get this bound. So you have a privacy amplification protocol, use random hashing, and the size of the output of the privacy amplification, or the rate of it, is given by RPA here. And the quality of the output is described by this side. It's basically equivalent to the fidelity. And then it's related to this rate by this bound, and here's another Renes entropy with different arrows and stuff. Okay. So then by the certainty relations, we can relate this to the error probability of the coding task. And there's an inequality here because we actually have to convert. Remember, the guessing probability will be related to the fidelity. We've got to convert that to the relative entropy. And then we have to continue using dualities on the other side because we're not interested in bounding, we don't want a statement about the coding problem in terms of something to do with privacy amplification of this sort of dual setup, this other observable. So we can actually use entropic uncertainty relation again to convert this back into something that involves the Z measurement on system A. So if you look here, the other thing I should emphasize is there's a lot of symbols here, but this is the output of the protocol, and it's measuring the quality of it. Is it good for what you want, privacy amplification? This is a statement about a property of the input state. So here's the output on n systems. You have to process them in some way with the hash function. But this is just the input, the single input. You compute this Renes entropy from the single copy. Okay. So here also you can, now we've got the rate of the information reconciliation protocol, and this is another duality. Okay, so that's for Renes entropies. Okay, then you convert this back to channel coding, and you actually get very close to the result that we want. So if you remember what the expression was in the very beginning, I told you, what we get here from this procedure is something that works for channels where the optimum input distribution, that's right down here, is uniform. Okay, so for instance, channels with certain symmetry will have this, this optimizer will be uniform, and then our construction works for those. We get the correct error exponent, the error exponent that Holevo conjectured. Okay, so now we need to do a little bit more work in 10 seconds to get the other case. So what happens when that distribution is not uniform? Well, we basically hack our way to get to the uniform case. So one thing you can do, so now if we don't have the uniform distribution is not the optimal one, or the optimal distribution is not uniform, we can either use a type class argument on blocks, that's what Li and Yang did, or we can quantize okay, that's confusing in this context. We can discretize, that's the approach I did. Okay, so let me, in 1 minute, tell you at least what they did, since they're not here to tell you about it. So if you have some other distributions not uniform that you want to emulate in this scheme, what you can do is just collect a bunch of the channels together and consider many inputs. So here 3, and you can just look at type classes in that, and you can just pick the one which it looks most like the distribution that you want to have. And then you just encode into that type class uniformly. That's what this arrow here, this big arrow, means there's more inputs on this side than to these channels. And once you've done that, the whole thing is a new channel, W prime, where it kind of looks like locally in the outputs here, you're getting the distribution that you want. Sorry, it looks like that the inputs were the distribution that you wanted, because it's basically like the empirical distribution of this whole block. And they prove a little lemma here that relates the Renes entropies in these 2 different cases, so that you get the quantity that you want. Okay, and now since I'm really kind of out of time, I'll skip the one that I did. Actually, I showed the picture of Gallagher in the beginning, and the problem was I had this result for the symmetric case, and I forgot to continue reading in Gallagher's book where he does this kind of quantization, and you can sort of see a little picture of it here. And yeah, so you can kind of just, it's kind of based on Gallagher with a bit more of the mathematical detail put in. Okay, but in the end you get the correct error exponent that you wanted. Okay, so I think I need to stop there, and if there's some more proof details if you really want to know. So thanks.
Any questions?
This there is entropic uncertain relation with Renes. This is our result with Mario.
Yes, the one that I need to use. Sorry, I should stand over here. The one that's used is the one with you and I think with you and Marco and Mario, if I'm not mistaken.
Okay,
yes,
okay.
yes. So that's, whoops, just to be concrete, this one, right, to convert from tilde down to bar up. Yes.
Thanks for the talk. I'm sort of trying to understand why conceptually this doesn't work for like a fully quantum case, because what's the barrier? Is it just the distribution reshaping? Because you still have like a singlet fraction interpretation with a duality and a decoupling.
I think, well, it's actually kind of, okay, so this was like the simplest coding problem, I would say, because it's like classical quantum.
Sure.
But the proof, like, just using decoupling for a coding theorem is actually more straightforward as a proof technique, and that works for the quantum case.
Right.
This is kind of like decoupling, right? Because you're doing some privacy amplification.
No.
But because of the classical nature of the input, it's kind of, you have to work with these uncertainty relations instead of just straight decoupling. Now, if you want to do the quantum case with decoupling, then you're just looking at kind of error. I mean, you'd be looking at the dual problem, like the decoupling problem, but I think there that, well, there's some barrier to doing it. I'm not entirely sure what that, well, I think, so you can't just use, okay, I'm not entirely sure what the barrier to doing it is, but
Okay.
I think it's not, somehow it doesn't come together as well as in this case.
Okay. Thank you.
Is there any hope to extend this result to the universal coding setup?
Universal coding. So when you want to not know only know the capacity of the channel or something,
Yes,
and not
yes.
I am not sure about that. I guess Yeah, I'd really have to think about that. I have never really thought about it before.
As you know, before your result, I already obtained the exponential degree rate for error probability, but my exponent is not tied.
Right.
So that exponent can be maybe very close to that exponent can be attained by using a universal coding.
Aha. Okay. So there's a different expression.
Yes, so weaker one, not tight one.
Right. So a different Renes here, as I recall, maybe not optimized or something.
Not optimal.
But you're saying it will get the universal.
Universal, yes, I
Yes.
already
I see. I see. So perhaps that's optimal for the universal case. I don't know.
So I have one question. So from your result, do we know that can we use random codes at the input, at the encoder, and with some optimal POVM or suboptimal POVM corresponding to those random codes can achieve this error?
Yes. So right. So okay. Indeed, so the reduction was through these hash functions and so on. Here we're using hash functions. So you can actually use linear codes. You can even have some structure on the codes, like these modified triplets, hash functions. So a subset of linear codes. So you can have linear codes. The statement at the end, though, is going to be about the optimal decoder. So I have no idea about the structure of the decoder. Okay. But you can have quite a lot of structure of the input, on the input side of the encoder. You only need linear codes.
But so
Did that answer your question? Maybe not.
but do we know the structure of those input linear codes at the input?
So, right, you don't have to. You also don't have to use just random linear code, all possible random linear codes. You can have these triplets. Linear codes that kind of correspond to these triplets hash functions. So modified triplets hash function, which is
A kind of construction.
it's a much simpler class than all linear codes, but it's not. I don't know. It's not the most natural code, for communication or something. It's a sort of convolution, but with giant blocks. So.
Okay, so let's thank Joe and all the speakers of this session again.
Thank you, everyone. Just a reminder, today the event registration and information desk will be closing at 5 p.m. sharp. If you have any luggage or posters, those posters will be discarded at the end of our sessions today. So please come by before 5 o'clock. Thank you for attending.
I wasn't sure how it was going. I thought it would go good.